Did you know that in microgravity you can better study liquid metals and how they solidify? Humans started using metals more than 5,000 years ago. It comes as no surprise that we now find metals and metallic alloys all around us. From utensils, smartphones, and body implants, to cars, airplanes, and spacecraft. Despite the ubiquity of metallic materials, there's still a lot we don't know about them. To this day, there are details of solidification that remain unknown to us.
To create metallic alloys and subsequently turn them into useful objects, they must turn from a liquid to a solid state. It's much like baking a cake. At first, we mix all the ingredients, then we pour them into a mold where they bind and solidify to create a final product. But on Earth, because of gravity when liquids solidify, the newly formed crystals move away from the region where they first appear and may even remelt, which makes it hard to distinguish which phenomena are caused by gravity and which are caused by the solidification process itself.
An X-ray technology, similar to the one used in medicine to image bones, is offering a step forward in materials science research. It shows in real time how metals transform from a liquid to a solid state.
In our experiment, we melt samples of aluminum copper alloy at 700 degrees Celsius and then quickly cool them down to observe via X-ray videos how they solidify in real time. Specifically, we look for structures called dendrites. Dendrites can grow in one direction like trees or equally in all directions like snowflakes. And it is very important to control the microstructure of metallic alloys because it determines the properties of the final product. For example, tree-like structure is better for turbine blades, and snowflake structure is better to produce car engines. We have performed several experiments in parabolic flights and sounding rockets, and we can now better understand which of the effects that we observe on ground are caused by gravity and which are caused by the solidification process itself. Eventually, it helps the industry to adjust their models and simulations to reduce scrap rates and manufacturing costs.
Besides understanding how metallic alloys solidify, it's important to know their properties. We can easily measure viscosity, thermal conductivity, and density of solid metals, but when they're in a liquid state, gravity distorts their shape, making it hard to precisely measure their properties. Microgravity on the International Space Station removes this obstacle.
We use an electromagnetic levitator on the ISS to levitate spheres made of metallic alloys. Using an electromagnetic field, we can heat and melt the spheres that are about 7 millimeters in diameter. The electromagnetic levitator allows us to heat the liquid samples to about 2200 degrees Celsius. We can modulate their temperature or let the liquid samples oscillate to obtain key properties such as surface tension and viscosity. In conventional ground-based experiments, these measurements are unreliable or impossible due to reactions with the sample container. For our measurements, we need to have a perfectly spherical droplet, good control over its temperature, and we want to control the fluid flow inside the droplet. This is only possible in microgravity. We have already done some benchmark measurements on high-temperature materials, such as nickel, zirconium, and titanium-based alloys, and also on steel. The results are now used, for example, to improve the casting process of turbine parts for aircrafts with reduced CO2 emissions. Our results help also to build stronger, lightweight constructions in the transport sector and to optimize 3D printing of metals for tailor-made biomedical implants.
We at Tata Steel produce steel for several applications for worldwide markets like automotive, white goods and yellow goods, building applications, and the food and canning industry. We have been using the electromagnetic levitator on the International Space Station to determine properties for new steels, where the effect of some elements on the solidification is not well understood. The difference with experiments on ground is that they suffer from rapid surface oxidation, and together with the gravitational forces, causes non-uniform conditions on the material to be tested, giving no representative values. So the advantage of testing under microgravity is having high accurate measurements without any interaction of gravitational forces and oxidative atmosphere. Using these properties to validate model calculations and predict how to produce at an industrial scale is allowing Tata Steel to optimize the production of steel and know how to cast a new steel first time right.
Numerous industrial applications can benefit from metal alloys research in space, from engineering in domestic appliances, vehicles, and lifts, to medicine and implants, and the environment in turbines and blades. It might help to improve production processes and enhance properties for stronger, lighter, and durable materials. With the knowledge that space can help further study liquid metals and how they solidify, do take advantage of the opportunities to develop your research and extend your achievements. Take the next step, the step to space. We already have.